Okay, hello, glad to be here to talk about one of my favorite areas on the moon, Rhino Gamma with MCube. Next slide, please. Rhino Gamma is a prominent magnetic anomaly in Oceanus Procellarum. There are other magnetic anomalies that are not associated with swirls, but Rhino Gamma is one of the case type areas for swirls. It's also going to be one of the landing areas for the NASA CLIPS program in a few years, so stay tuned. Next slide. Rhino Gamma terrain, this is a high albedo, high sun image of Rhino Gamma. Next slide is a low sun image, and you can see the shadows and craters, but you see no shadows on Rhino Gamma itself. Next slide. There's essentially no anomalous rock abundance associated with Rhino Gamma. Next slide. The terrain, there's nothing there. Let's go to the next slide and we can step back and look at this area in broader context. Over on the left is highland terrain, up to the north is Marius Hills, or the crater Reiner, and Rhino Gamma is right in the middle of this vast volcanic plain with nothing else there. Thank you. Next slide, please. Well, what are these swirls? Well, they are clearly albedo variations. They're not associated with compositional variations, nor are they associated with what's been exposed relatively recently. And I can show you examples of that in a moment. What they are associated with is magnetic anomalies themselves, and that's the key. Next slide, please. Okay, we're going to look at MCube data for Rhino Gamma. There's several sequences acquired with MCube. The first one was at high sun. However, that's very thermally challenging for MCube. The other is low sun, which it means the signal is diminished. We're going to look at the nice intermediate sun, but we only have one strip. Next slide, please. The strip is 40 kilometers across. We're going to look at the non-swirl area to the south and then concentrate on the swirl itself and the properties that we can see in MCube data. Next slide, please. This gives you a overview of two traverses across a fresh crater and a larger crater that has steep slides and the exposing fresh material. And we can look at the overall properties. Next slide. And the properties for fresh material is that it's bright at all wavelengths, it's bright at visible wavelengths, much brighter than the background soil, which is the dark spectra. But at longer wavelengths, there's pyroxene absorption bands, mineral absorption bands that are very distinctive. And at that wavelength, 2200 nanometers, the fresh material is lower than the background material. This is similar for the larger crater, crater A, and we won't discuss that further. Next slide, please. However, the swirls have quite different properties, and we have two traverses that we're going to look at for the swirls. The first one is on the left, and I've split apart these traverses to have the northern part to the background dark soil, and then the southern part starting with the same dark soil going to the south. And you can see that the properties are the same on both sides of the dark lane, it's called. And the dark lane essentially looks like our mature soil that we were talking about before. The second thing is that there's a small crater in the northern part, but it doesn't get, it only comes to the background soil of the swirl. Next slide, please. So swirls are brighter at all wavelengths. They have a steeper continuum, which we interpret as nanophase iron, very tiny metallic iron developed during soil processes. However, what causes the brightness appears to be a lack of a absorbing material that has neutral spectral properties, so it doesn't have any effect on the spectrum. These are typically the larger particles, the micron size particles. Next slide, please. Okay, let's look at the second traverse across the swirl. Yeah, again, I've highlighted it north and south portion. The northern portion essentially starts at a fresh crater and continues down through some form of mixed zone to the background soil. Again, starting with that same background soil going into the swirl, we see the basic properties of the swirl itself, including a small little rim of a crater that never gets below the background of swirl materials. Next slide. So here's a summary of what the properties of both the swirls and the immature soil are. You can visually see they're quite different. Swirls have a steep continuum linked to nanophase iron. They're brighter at all wavelengths, and they lack, to be bright, they probably lack a absorbing component that has no spectral character. The immature soils are bright at visible wavelengths, but have absorptions that occur and make them darker at the longer wavelengths, and they have a flatter continuum. Next slide, please. Now, are these properties representative across the swirl? And that's what I'm going to be talking about next, to show you that, yes, they are. Next slide, and we'll have to go through these very quickly. First of all, here's the two wavelengths we were looking at, the 750 and the 2200. If you look closely at the Mare areas in the south, you can see, yes, indeed, the fresh crater has a very low signal at this wavelength, similarly with the areas that we were looking at the north. But you can also notice that within the swirl, the fresh craters appear to almost disappear, or the moderately fresh craters appear to disappear. Now, I'm not going to talk about the thermal properties, which I've highlighted in the red because we don't have time, and that's calibration that we can't address. Next slide. What we will talk about is the continuum, and we'll talk about two different ways of looking at the continuum. This is the classic way where you have a continuum slope, delta x over delta y. It's a mathematical measurement, and it has a clear distinctive properties. You can see down at the Mare areas, it nicely picks out those things that have a flat continuum as being dark very nicely. Let's look at the second mode for continuum. In the next slide, please. This is a continuum ratio, which is the common way of looking at the continuum. However, it's quite different mathematically and consequently spatially than the classical continuum slope. And the characteristics that you can see if you look at what we call the neck, the part that starts in the middle and goes off to the right, it's quite a different distinction between the two ways you measure the continuum slope. I'm going to compare in the next slide this with the OH absorption that MCube can measure. And for those of you who aren't familiar with this, swirls have a very low abundance of OH, primarily due to the fact that they're shielded by the magnetic field, and you don't get solar wind interacting. What I like about, or what I'd like to illustrate here, is that the shape of what we see in that neck part is comparable to what we see in the neck, which argues that it's associated with magnetic environment. Next slide. Okay. There we have a quick tour around Rhino Gamma with MCube. Okay.